Hello children, welcome back to the channel. Up till now we have discussed the Newton's law of gravitation, and also we have seen the vector form of it, and also discussed about the shell theorem of Newton's, wherein we have seen that gravitational shielding is not possible. All these things are discussed in the first two videos on gravitation, the link of which will be given in the description below. You can refer to them always. Now, today we will be discussing about the gravitation of Earth, and specifically about the acceleration due to gravity, which we have been using since the chapter on linear motion, that is kinematics, in one dimension as well as in two dimension. Okay, like the projectile motion in the Newton's law also we have used acceleration due to gravity. Now let us see what is the origin of acceleration due to gravity. For that, we will start with considering that Earth is a sphere. Okay, it's a roughly spherical, right? And we will assume that the average density of Earth is same all throughout. Though it is not the case, we know that the outer crust of the Earth is lighter compared to, has less dense compared with the inner cores of the Earth. But we will say that Earth has an average density, and let's say that density is given by rho. Okay, and let's say the radius of Earth is capital R, which means mass of Earth m will be given by 4 by 3 pi r cube, that is the volume of the sphere of radius r, multiplied by the density of Earth, and so we get mass of Earth to be 4 by 3 pi r cube into rho. Now from law of gravitation we know that Earth, due to its mass, will pull any object towards its center. Right. So let's say first the object is outside the Earth's surface. Say we have an object of mass m outside the or above the Earth's surface, and so from the center of Earth to the object, the distance we will take it as, say, r. So from the center of Earth, not from the surface of Earth. From the surface of Earth, the distance will be less, right? This distance will be r, and this distance will be some other thing. That will be capital R, small r minus r. So we are talking about the entire length. So if it is so, then we already know that from shell theorem that if an object is outside the body, spherical body, then the entire spherical body will act as if the entire mass of the body is concentrated at the center, and that is why the distance from the center to the object, which also will act as if its own all masses, entire mass is concentrated at the center of mass of the object. So from the center of mass of the object to the center of the Earth, which is also the center of mass of the Earth, Earth being a sphere of uniform density. So this center to this center, this distance is important, and that's why we have spoken about this distance r. So outside the Earth's surface, at any, if an object is placed, and if the distance of the object from the center of the Earth is r, then we know that force of gravitation in magnitude will be given by g capital M small m, the mass of the smaller object, divided by r square, not capital R this time, since this is this distance is smaller, so it will be small r square. Okay, but what if we consider something inside the Earth's surface? That is, what if the object not being outside but is inside at some height, say r, or at a distance of r from the center of Earth, but it is now inside the Earth. In other words, what we can say is that what if the object is not outside the Earth's surface but at certain distance or certain depth of d from the Earth's surface. Okay, so this is the surface of the Earth, the object is at a distance depth of d. So clearly this depth d is equal to radius of Earth minus the distance of the object from the center of the Earth. Now we can consider a concentric circle having radius r, having the same center as the earth. Okay, so this object is now at the surface of the inner shell or inner sphere. We have already seen in the previous video about the shell theorem that the mass above the or outside this sphere, the mass will not affect the object. Only gravitational force will be given by the inner core or the mass inside the surface, inside the radius smaller, that is where the object is placed. So if we consider the inner sphere, then this inner sphere will have certain mass, right? Let's call this mass m r for this inner sphere. Okay, so applying shell theorem, what we get, the force of gravitational attraction will be given by g m r m by r squared. Same. Okay. However, now instead of capital M, the entire mass of the earth, we consider a mass of the inner sphere. Now what will be the mass of the inner sphere? That will clearly be mr can be written by 4 by 3 pi r cube into rho. Right? So if we compare it to this, so what we have, capital M by small m, mr will be 4 by 3 pi capital R cube rho and divided by 4 by 3 pi capital R cube rho, which means 4 by 3 pi and rho will cancel and we will have capital R cube by small r cube. Or we can say that mr can be given by small r cube by capital R cube into capital M. And if we substitute that value here, what do we get? We get g small m by r squared, and then we substitute this value, that is mr, that will be r cube by capital R cube into m, which will simplify to g m by capital R cube into r, as we have found already. Okay. Now, if instead of the object being inside, what if the object was on the surface? On the surface of the earth. So clearly, for the surface of the earth in this equation, what we will have, smaller equal to capital R. Because on the surface means d is 0, depth from the surface will be 0. If d is 0, we get smaller equal to capital R from this equation. Therefore, we have F equal to Gm by, small m will still be there, right? Gmm by capital R square. Okay. So, if the object is far away from the earth's surface, force will be given by this. If the object is below the earth's surface, the force of gravitational attraction will be given by this. And on the surface, or if the object is very near to the surface of the earth, wherein this height, variation of the height can be negligible compared with the radius of the earth, then we have F equal to this. Now this third equation becomes very, very important for us. How is that? Okay, for that, I keep this equation for the time being. So what we have gained is that on the surface of the earth or near the surface of the earth, F is equal to gmm by r square. However, we already know about the acceleration due to gravity. Acceleration due to gravity is the acceleration with which an object, when released near the surface of the earth, will accelerate towards the earth's surface, right? So, which is given by small g. You remember that? Okay, now if the object of mass m was here, very close to the earth's surface, and we apply this expression, that is to say, if its acceleration is g, mass is m, then the force that is applying on this will be equal to mg, which is known as the weight of the object, right? Now, the weight of the object is due to mass into acceleration due to gravity. However, the force, this force is basically the force of gravity of Earth or the force of gravitational attraction of Earth, which means this force given by this expression, weight of the object, and the force given by this expression, these two forces must be equal, right? This gravitational attraction gives us the weight of the object. So, if we compare these two, what we get? 1 and 2 will give us mg must be equal to g capital M small m by r square. That is to say, g will be equal to gm by r square. Fine. So acceleration due to gravity is given by this expression, where m is the mass of the Earth and r is the radius of the Earth, which, if you consider Earth to be a sphere, uniform sphere, will have to be a constant, and that's why most of the cases we have taken acceleration due to gravity to be constant, and we have taken it to be equal to, almost equal to 9.8 meter per second or meter per second square. You can substitute the value of universal gravitational constant, mass of the Earth and radius of the Earth from known chart, and you can find this value. Okay, now since g is this, and we can experimentally measure the acceleration due to gravity by looking at falling objects, which we have found to be 9.8 meter per second square already, 9.81 meter per second square. Anyways, so this gives us a very good tool to find the mass of the Earth. How? By cross multiplication, we can say that m equal to g r square by universal gravitational constant. So, if it is so, we substitute the value of g, the radius of Earth, the average radius of Earth is almost 6,400 kilometers, that is to say nearly 6.3637 10 to the power 6 meter actually. 6.37 into 10 to the power 6 meter. This is radius of Earth, and universal gravitational constant you already know, 6.67 into 10 to the power minus 11. Okay, so if you substitute the values, you will get mass of Earth, which will turn out to be around 5.97 into 10 to the power 24 kg. 5.97 into 10 to the power 24 kg, or which is roughly equal to 6 into 10 to the power 24 kg. Okay, now we know that mass equal to 4 by 3 pi r cube into rho. So, if you use this, instead of mass, if you use this equation and equate it with gr square by capital G, we will also get that rho will be given by 3 by 4 g r square by g, and then we have 1 by pi r cube, or 4 g sorry, not 4, this will be 3 by 4 g r pi, 4 pi r g. Okay, 3g by 4 pi r g. Substitute the value r is already given, g you already have found, and so this will give us that density of art is nearly equal to 5500 kg per meter cube. 5500 kg per meter cube. See, this density we have found by assuming that the earth is a uniform sphere, that is the mass or density of the earth is constant throughout its, and from the surface to the center the density doesn't vary, but which is not the case as we already know. So what we will find is that actually the density of the outer crust or outer side of the earth will be much less compared with 5500 kg, and density of the earth at the core of the earth is to be found to be much higher than this, so that the average density turns out to be this much. Okay. Try to tackle certain numericals. Okay, a few numericals. Number one, question number one or problem number one is that if a body weighs 90 kgf, kilogram force, 90 kg force on the earth's surface, on the surface of the earth, how much will it weigh on the surface of Mars? Sorry, Mars, on the surface of Mars, whose mass is 1/9. One by ninth of the mass of Earth, and whose density or radius is half of that of Earth's radius. So weight of an object on the Earth's surface is given. We want to find the weight of the object, same object on the Mars surface, where mass of Earth is Earth is 9 times. That is, mass of Mars is 1/9 times the mass of Earth, and radius of Mars is half the radius of Earth. So clearly weight will be given by mg, right? Mass of the object into mass of the acceleration due to gravity. So weight on Earth will be mass of the object into gravity, acceleration due to gravity on Earth's surface. Weight on Mars will be mass of the object into acceleration due to gravity on Mars surface. Therefore, Wm by We will be simply Gm by Ge, because m's will cancel out, which will give us weight on Mars surface will be G acceleration due to gravity on Mars surface divided by acceleration due to gravity on Earth surface multiplied by weight of the object on Earth surface. Okay, now till now this value has been given already in the question. We haven't found Gm and Ge. However, from the discussion that we had just now, we already know that acceleration due to gravity on any planet will be given by Gm by radius of the object of the body squared, right? So if I say it is Earth, then mass of Earth by radius of Earth squared, and for Mars it will be Gm will be capital G m of Mars divided by r of Mars squared. Given, what are given? That mass of Mars is mass of Earth divided by 9 times, and mass of radius of Mars is radius of Earth divided by 2 times. So if you substitute these values here, what do we get? G, instead of mass of Mars, we can write mass of Earth by 9, and then radius of Mars will be radius of Earth by 2 square, which we will get Gme by Re. 2 square 4 will go in the numerator and it will come in denominator. 9 will come in the denominator. But Gm by Re squared is acceleration due to gravity on Earth's surface, which means that this is equal to Ge, 4 by 9 times of Ge, right? Therefore, Gm by Ge that we need to solve this problem will be given by Gm by Ge will be 4 by 9. So what we have found? We have found Gm by G, we have found Wb already has been given, weight of object on the Earth's surface, so we can clearly now solve this problem. Weight of the object on Mars will be Gm by G, which is 4 by 9 times weight of the object on Earth's surface, that is 90 kg force, which will be 40 kg force, and that will be our required solution. Okay. Now, next problem is, if radius of Earth reduces or shrinks by 2%, R reduces by 2%, the mass remaining the same, the mass doesn't change, then how will G change? That is acceleration due to gravity change. So what we have been given is that radius of the Earth has been reduced by 2%. We need to find what will be the variation in acceleration due to gravity. Okay. Now, to solve this problem, what needs to be done? I leave it up to you. I am not going to solve this problem right now. What I would ask you to do is that solve this problem on your own and then put the solution in the comments. Okay, we will see whether you have found the correct solution or not, and we will discuss this in the next video. While on it, I will add another problem for you to solve at home. That is the kind of problem we have already solved way back in class 9. The problem is that a man can jump 1.5 meter high on Earth. A man can jump 1.5 meter height to up to a height of 1.5 meter on Earth's surface. What would be the approximate height he would be able to jump in a place or in a planet whose density is 1/4 that of Earth? Density of planet is 1/4 of Earth's density, and whose radius is 1/3 of Earth's radius. Radius is 1/3 of Earth. So a man can jump 1.5 meter to a height of 1.5 meter on the Earth's surface. Up to what height, approximate height, he will be able to jump in a planet whose density is 1/4 times that of the Earth and whose radius is 1/3 that of the Earth. Okay, so these two problems you need to solve at home, and the solution, please put the solution in the comment below so that we can find the final value in the comment below, so that I can take it up or take those in the next video.